I'm sure you've seen the snowy blizzards, the cars stuck in ditches, and the late night snow snacks. We live in Calgary, so trust me when I say that we get a lot of snow. To be exact, almost 128.8 centimeters per year. Ever since I was young, I've always been really interested in renewable energy. 2 years ago, when I was moving into a new house, my family decided to invest in solar panels. But everyone I talked to always asked, why are you even getting solar panels installed? Will they even generate electricity during the winter? Hi everyone, my name is Arushi Bhargav, and today I'm here to talk to you about the effect of weather on the electricity generation of solar panels. Let's start off by talking about my research. The first thing I'd like to do is introduce how solar energy is produced. Solar cells are made up of a lattice of silicon. One side has excess electrons while the other has a deficiency of electrons. The difference in charge creates an electric field between the two layers such that electrons can move across, as shown by the arrows. So, when a photon strikes a silicon cell with enough energy, it can knock an electron from its bond in the negative layer, which leaves a hole and an extra electron. The electron will begin to move, creating a flow of electrons. This is then collected through thin metal wires at the top of the cell. This electricity can then be used. These small individual solar cells are then connected to form bigger modules to generate greater amounts of electricity. Currently, there's very little statistical analysis on the full extent to how weather impacts solar production. However, sources suggest that solar panels will work well in clouds, rain, and fog, though it is not as much as the electricity that would be generated on a clear, sunny day. It is also suggested that the snow that lands on the surface of solar panels actually has a significant amount on electricity generation. Finally, extreme temperatures are not ideal for solar panels. A cooler, sunnier day is much more beneficial. In this project, the question that I tried to answer was how and if weather impacts the amount of electricity that is generated by solar panels in Calgary. I hypothesized that solar panels will generate an adequate amount of electricity for a home in Calgary, which would be approximately 7,200 kilowatt hours per year, regardless of the varying weather conditions, including temperature, visibility, precipitation, hours of daylight, solar radiation, and cloud cover. My project was mainly data-based. This meant that I collected data and did a statistic analysis to determine if there was any correlation between the weather and the electricity generated. The electricity generation data was sourced from my own house and the solar panels on my roof through the SolarEdge app. The weather data was collected from the Calgary Weather Stats page and the Government of Canada's Historical Climate Data website. To determine correlation, some statistical analysis was used. This included analyzing general trends in the data of weather factors in electricity generation over time, as well as an analysis of the trends of the correlation between each independent variable and the dependent variable. Mathematically, the R factor was looked at, as well as the R squared value. The R squared was the main statistical measure, as that it tells us how much one variable can be explained by the other, which ultimately tells us how related or unrelated two variables are. In my experiment, the independent variables were temperature, precipitation, hours of daylight, solar radiation, and cloud cover. The dependent variable, or responding variable, was solar energy production in watt hours. The controlled variables included the number of panels, the angle of panels, as well as the specific type of solar cells. In this experiment, Q-antum cells were used. They are a type of monocrystalline solar cells with an efficiency rate of up to 20%. Data was collected over 82 weeks and 4 days. This meant that data was collected from August of 2019 to the end of February in 2021. Let's discuss some of the results that I found from this experiment. This scatter plot shows the correlation between temperature and electricity generation. As you can see, there's a positive slope between the two variables. This indicates that as temperature increases, electricity generation also increases. It is also important to note that once temperatures reach below -20, there's little to no electricity generation. The R-squared value between the two variables is 0.47. This means that there's a moderate correlation between the two variables. This graph shows the correlation between precipitation and electricity generation. There's a negative relationship between the two variables, as seen by the trend line. When there's little precipitation, there's more electricity generation, and vice versa. However, it is important to note that even when there is greater amounts of precipitation, significant amounts of electricity were still being produced. To determine whether or not there is actually correlation, we can look at the R-squared value, which is 0.02. This indicates that though there seems to be a trend in the data, the trend is not statistically significant on the electricity being produced. To investigate the correlation between the two variables, the graph of solar radiation and electricity generation can be analyzed. There's a positive relationship between the two variables. This means that as one variable increases, the other also increases. The R-squared value is 0.45, suggesting that there is a moderate correlation between solar radiation and electricity generation. The trend line for daylight also followed the same pattern. In fact, the R-squared value was also 0.45, indicating that daylight and solar radiation are likely connected in the way that they impact electricity generation. In analyzing visibility and electricity production, it can be seen that there is a positive slope. The R-squared value is only 0.23, which indicates that the relationship between the two variables is not significant, and though there is a trend, it is not representative of all of the data. This scatter plot shows the inverse relationship between cloud cover and electricity generation, which is what would be expected. However, the R-squared value is only 0.13. This means that only 13% of the data can be explained by this trend. Though the graph shows that there is an inverse relationship between the two variables, it is not statistically significant. This is a table of the statistical analysis that was done. The rightmost column shows the correlation percentage ordered from least to most. The lowest was precipitation, which only had a correlation of 2%. This can be explained as the experiment was done on a daily basis, and precipitation only lasts usually for a couple of hours. So even if there were large amounts of precipitation, there could still be sunny weather later in the day, meaning that electricity can still be generated. The variables with the highest correlation are solar radiation, daylight hours, and temperature. In this presentation, only the correlation graphs were analyzed, but in the full experiment, each of the independent variables and the dependent variable were compared over time. These three variables were related to the rotation of the Earth. They each followed a trend where they were higher in the summer and lower in the winter. This indicates that the availability of sunlight and the temperature has the most correlation to electricity output. After doing some calculations, I found that the total electricity generated can account for one whole household's electricity, which on average is 7,200 kilowatt hours. In addition to this, 58% of another household's electricity can also be covered per year. This is compelling evidence that solar panels are an excellent choice in Calgary, considering the large amounts of solar radiation and the positive environmental impacts. For instance, per year, the total carbon emissions that were displaced by this particular residential photovoltaic system was 6.48 tons of carbon dioxide. Considering that the carbon dioxide released during the manufacturing process of solar panels requires 52 grams per kilowatt hour generated in terms of carbon dioxide, this means that in less than 2.7 years, the total life cycle carbon emissions for the system will be covered. This highlights just how renewable solar energy is. In conclusion, none of the variables that were analyzed in this experiment had a correlation of above 50%. This indicates that there was no significant correlation. In Calgary, there's a common misconception that due to the heavy snow, cold temperatures, and little daylight, an adequate amount of electricity cannot be generated in order to power a home. However, we found that factors such as temperature, hours of daylight, and solar radiation have the greatest impact on solar electricity generation, as opposed to precipitation, such as snow. Furthermore, it has been proven that solar panels are still effective during the winter. The hypothesis is proven true because regardless of the weather, the solar panels were able to produce 7,200 kilowatt hours per year, which is enough to sustain the average home in Alberta per year. Here are my references. Thank you for listening.